Hi, my name is Leah Kiner, and I'm going to be presenting the work titled Multi-Body Prescribed Spacecraft Dynamics Subject to Actuator Inputs. So the motivation behind this work is the complexities arising from simulating different types of actuated spacecraft components that can be connected to the central rigid spacecraft hub. And some examples here are actuated solar arrays, motion platforms, robotic arms seen in the lower right figure, the Canadarm, gimbal thrusters, and communication antennas seen in the Cassini spacecraft. So the dynamics of these complex spacecraft components are non-trivial to simulate. For example, the relationship between actuator inputs and the states of the actuated component is often unclear. And three-dimensional solid models are commonly used to analyze these different types of articulated spacecraft components, where lookup tables are often provided by the actuator manufacturer. These lookup tables are very useful. However, only a limited amount of scalar information may be available from these tables. So in light of these complexities in simulating actuated spacecraft components, the focus of this work is to develop a profiler to determine the rotational kinematic states of a two-axis gimbal that is actuated sequentially by two stepper motors. And this statement is going to be unpacked in the following slides. So the problem of interest in this work is a two-axis gimbal specifically that is undergoing prescribed motion. And I'm going to be also talking about what this means in the following slides. But first, we can see here our problem setup, where we have a spacecraft hub in gray with a stationary body frame attached to it, and also with a stationary mount frame attached at the end. And our actuated two-axis gimbal is seen in green, where the body frame is the F frame. And the important part to note here is that the motion of the gimbal is defined relative to this fixed mount frame connected to the spacecraft hub. So two-axis gimbal is simply a gimbal that's whose attitude relative to the mount frame is expressed using a series of two Euler angle rotations. So first, when the gimbal is aligned with the mount frame, we take the gimbal through two sequential rotations. And the first rotation is characterized by an angle psi, and the second rotation is by an angle phi. So these are our gimbal tip and tilt angles, we call them. So for this case here, where we're rotating about the third mount frame axis by 90 degrees, our psi is 90 degrees. And then our second rotation is about our F1 axis by 45 degrees. So then our phi is going to be 45 degrees here. So we can either use Euler angles to describe the attitude of our gimbal, or more commonly, we can use those Euler angles to define the direction cosine matrix between our our gimbal's frame and the mount frame. So next, our gimbal is said to undergo prescribed motion. So prescribed motion involves the explicit definition of a rigid body states over a given period of time. So essentially what this means is that the dynamics of a prescribed body do impact the motion of the other bodies in our spacecraft system. However, the dynamics of our spacecraft hub and other bodies on the spacecraft are assumed to not impact the motion of our prescribed body at all. So we can explicitly define what the states of our prescribed bodies are. And we have this sort of one-way coupling that only really exists when the states of the prescribed body are impacting the dynamics of the rest of the spacecraft system. And we can see here that the prescribed parameters used to describe the full states of our prescribed body are, we have the translational states and the rotational states seen here. So to wrap up this discussion, the dynamics of stepper motors, articulated solar arrays, actuated platforms, gimbal thrusters, servo sensors, robotic manipulators all may be described through this concept of prescribed motion. So next, in this work, the gimbal is assumed to be actuated sequentially by two stepper motors. And this is important to note because we are not actuating the motors simultaneously at the same time. So the other important thing to note here is that assuming the correct number of steps that each motor has to take has been correctly determined, we can actuate the motors in any order and the gimbal will arrive to the correct final attitude that we desire. So we can actuate these motors in any order. And then to prescribe the states of our gimbal, we are using a motor to gimbal angle lookup table that is provided by the 2-axis gimbal manufacturer, where we have, for any combination of motor angles, we can determine the gimbal tip and tilt angles, those Euler angles. And for the case where the motor angles are not consistent with rows in this lookup table, as seen in red here, we have to interpolate to solve for those gimbal tip and tilt angles. And then finally, in this work, we are assuming that the gimbal's translational motion is not impacted by the motor actuation. So we're only considering the rotational motion of the gimbal. The formulation described in this work is encapsulated in this yellow module 1 called Gimbal Actuator Prescribed Motion Kinematic Profiler. And here we have 3 stages in this profiler that I'm going to be elaborating on in the next few slides. But first, as a general outline, we are assuming that we have a commanded number of stepper motor step counts. So each motor has an associated number of steps that it needs to take. And then we are going to analytically profile first the stepper motor states, and then using that information, we will analytically profile the gimbal's motion. And then with our gimbal profiled motion, we can then determine the rotational prescribed motion states of interest here, our sigma, our angular velocity, and our angular acceleration of the gimbal relative to the mount frame. And then this work is not focusing on module 2, but I wanted to highlight in blue, this is the multi-body prescribed motion dynamics simulation module. And this module was previously developed and implemented in Basilisk. And Basilisk is a fast, open source, spacecraft-centric astrodynamics simulation framework that is developed jointly by the AVS Lab and the Laboratory for Atmospheric Space Physics at CU. And when module 1 and module 2 are connected together, one can analyze the impact of a prescribed body's dynamics on the resulting spacecraft hub motion. So we can see how actuating a prescribed body will impact the motion of a spacecraft hub. But that is not part of the rest of this presentation. So first, stage 1 analytically profiles the stepper motor motion. So for a single motor step, the first thing that we need to do is solve for the time that this step is going to take. And this is going to be constant for every motor step. So we assume that we know the step angle of each motor, and this is the angle that the stepper motor rotates through for a single step. And we also assume that we know the maximum angular acceleration of these stepper motors. So once we solve for this time, a bang-bang acceleration profile is applied during each step. So during the first half of the step, we apply these equations on the left, and during the second half, we apply the equations on the right. And on the right-hand side here, we can see an example where we actuate motor 1 for 10 steps, and we can do the same for motor 2 as well. But this profile is characteristic of the behavior that we're looking to see here for our stepper motor. So now that we have a way to obtain the scalar states of our stepper motors for any number of steps, we then can discuss developing the analytical profile of the gimbal's motion. So first, it's important to note that the true gimbal path for each motor step is really unknown. And this is largely because the motor step size is often several orders of magnitude smaller than the step size given in the table of lookup table data. So between discrete points in this table, the gimbal's motion is really unknown. So here we're making an educated assumption that the gimbal most likely follows a rotation about a principal angle and through a principal angle about a principal axis E hat. And this is a characteristic of principal rotation vector parameters. So now we can use the lookup table data to determine the gimbal tip and tilt angles for any combination of motor angles. And then from our gimbal tip and tilt angles, because we know that those are Euler angles, like as we discussed earlier, we can then transform these Euler angles to principal rotation vector parameters, this phi and E hat. And it's also important to note that when our motor angles don't exactly match a row in this table, we need to interpolate, and we don't want to interpolate the angles separately. So instead of directly interpolating this psi and phi, we would choose the neighboring rows bounding this red row, and we would then convert both of our tip and tilt angles to principal rotation vectors. And then from these two principal rotation vectors, we can find a relative principal rotation vector to interpolate so that we only are interpolating a single angle. And then with our interpolated angle, we would do principal rotation vector addition to the smaller of the two rows in our table to get our full interpolated principal rotation vector. So that process is outlined more in the paper. However, at the end of this step, we will obtain our initial and our final gimbal attitude in terms of principal rotation vector parameters. So with these two principal rotation vector parameter sets, we can subtract them. And this isn't truly subtracting them. There's a formula for this. So once we subtract these parameters, we end up with a reference angle that the gimbal needs to move through during a single motor step to be driven to the correct attitude. And to drive the gimbal through this reference angle, we are going to apply a second bang-bang acceleration profile by solving for this gimbal angular acceleration. And the important thing to note here is that the gimbal and the stepper motor both need to move through a specified angle in the same amount of time, delta t. And we saw in stage 1 that we solved for the required motor step time. So this acceleration equation here uses that same motor step time to solve for the required acceleration that the gimbal needs. So we can see again that on the left side, during the first half of our motor step, we apply those equations, and then for the second half of the step, we apply the equations on the right. And then the result of stage 2 is a history in time of the gimbal's principal rotation vector parameters. And we also have the scalar principal angle rate and acceleration as well. So finally, stage 3 determines the prescribed motion states of the gimbal. And we can recall that the translational states are constant in this work. So we only need to solve for the modified Rodriguez parameter attitude set of the gimbal and the angular velocity and the angular acceleration of the gimbal. So we can use these 3 simple equations here to solve for those prescribed states at any given moment in time. So now that the profiler has been created, we simulated a gimbal thruster pointing scenario where the thrust direction along this F3 axis of the gimbal is commanded to actuate between 2 different attitudes. And another important thing to note here is that traditionally gimbal thrusters have a certain operational window where they can only actuate within a certain pointing range. So for this example, we bounded psi between -25 and 25 degrees and phi between -30 and 30 degrees, as seen in this figure on the left. So the gimbal is restricted to move inside this red boundary. And then the gimbal is commanded to actuate from one pointing extreme to the other, as seen in the green initial dot and in the final pink dot. And choosing the parameters in the table here, we determined that the number of steps to drive the gimbal to the final attitude for each motor is 256 steps. The step angle for the motors is 1/2 degree, and the step size in the table that we used is 2 degrees. So with all of the given parameters here, we first simulated an example where we actuated motor 1 followed by motor 2. So here's the attitude history of the gimbal and the angular velocity and angular acceleration. And what's interesting to see here is that when we fully actuate each motor separately, the gimbal follows the uppermost portion of this boundary. And if we were to actuate motor 2 first, followed by motor 1, as we'll see in the next slide, the gimbal will follow the bottom portion of this diamond. And some interesting results we wanted to show here was that still while actuating each motor separately, if we break up the segments of motor actuation, we can actually see that the density of this space is varying depending on where the gimbal is located. So for example, during the initial period of actuation, for the same motor steps, the gimbal angles vary a lot less than when the gimbal is closer to the central portion of this diamond shape. So to highlight this a bit more, we can look at the purple line here, and we are having each motor actuate twice. So we're breaking up that 256 steps into 4 different phases of 128 steps. And we can see that during the first half of the motor actuation, the gimbal only moves about 1/4 of the way through the maneuver. And then for the second half of the motor steps, the gimbal moves almost the entire way through the desired motion, which is really interesting to see here. So in conclusion, the profiler that was developed in this work prescribes the rotational kinematic states of a 2-axis gimbal that utilizes a motor to gimbal angle lookup table. And the profiler can be readily implemented into the previously developed Basilisk prescribed motion module to simulate the dynamic coupling between a spacecraft hub and connected actuated body. And in the future, we would like to develop a formulation to simultaneously actuate both of the motors to make the trajectory of the gimbal less choppy and more smooth. And we also want to incorporate the motor's effect on the translational motion of the gimbal as well, because we are neglecting that in this work. And there are some effects of the gimbal translation from the motor actuation. And then we also want to enhance the dynamical model of the stepper motor because the profiler used in this work is very simple and not entirely characteristic of the electrical dynamics of stepper motors. So with that, thank you very much for listening. And if you have any questions, please feel free to email either myself or my co-authors, Dr. Cody Allard and Dr. Hans-Peter Schaub. Thank you.